How can we work out this probability here? What can you do? Well, we can't just do it by direct counting because they're all different, right? They're different. They're not equally likely. You can go back to this formula sheet that I mentioned. This would be a good strategy. You have a formula here for how conditional probability is related. Can you write out this formula, except don't use A and B, use the things we have on the question we have right now? Can you write out that formula for what we're doing? I will pause while we do that. What formula can I write out for this here? What do you think? It's A and 10. Probability of A and 10 over probability of which one? The condition, right? This condition or this part of it. Probability of a 10. What are those numbers? One of them we already worked out. One of them we already found. What did we find already? We already know this. We already know all the ways you can get a 10. We actually already worked out both of those things. Let's look back to this here. We need both of these together. We'll get rid of this because we don't need this anymore because we wrote that formula out already. What do we want here? What numbers do we want? Where is this probability of A and a 10? It's this 1 out of 6. I'm going to highlight the 2 out of 12 so I can make some sense of it. Okay? Where is the other thing? Where is this? Probability of a 10? Where is it? It is 5 over 12, right? It's that number. What you're doing is here, you're saying you're dividing two other probabilities. You're saying it's 2 out of 12 divided by what? Divided by 5 out of 12. Make a big line in the middle so you don't get this mixed up. Okay? My green moved here, but we can put it back again. You're saying it's this one out of that one. You're dividing those two. What this means here is, you know how they're not equally likely here? When you go through and work out these probabilities, you sort of made them, you're counting them as though they're equally likely. There's this much chance you're going to get a 10 and B. There's this much chance you're going to get a 10 and A. Given that you know a $10 bill is chosen. Given that a $10 bill is chosen, you know it has to be one of these two cases then, right? So the total that you're using is just the 5 times out of 12 that you get a 10. 5 times out of 12 you get a 10. 2 of those 5 times it's from A. 3 of those 5 times it's from B. That's where this 5 comes from. Does that make sense? We worked out that 2 out of 12 times it's a 10 and from A. 3 out of 12 times it's a 10 and from B. If it says, what's the chance that it's A, or what's the chance that it's from A given you got a 10? Given you got a 10, it's only going to be out of 5. This works out to 2 out of 5. 2 times out of the 5 that you get a 10, it came from A. Does that make sense? Yes, no, maybe? You're dividing two probabilities to get it, but that's what's happening. You're reducing the sample space is not 12 anymore. When you do 2 twelfths divided by 5 twelfths, what happens to the 12s when you divide that? They cancel out, they're gone. It's just 2 out of 5 then. It's like you're reducing the sample space is not 12 anymore. It's 5. The new total is 5. It's 2 out of 5. You can divide two probabilities to get that. You can use that. You can use those. You can use that formula. Probably is the best way to start here. Can you try this question right now? It's a similar. It looks totally different, but it's a similar thing. I would analyze it with a tree diagram. First, something happens, and then something else happens. Come up with some symbols here. I would use D for not disease, but defective. and not D for not defective. I would use a 1 for factory 1 and a 2 for factory 2. Company has 2 factories. Factory 1, factory 2. Just like pot 1 and pot 2, like the other thing. Then you have defective given that it's in 1, right? Or you have not defective given that it's factory number 1. I'm going to spread this out to make it a little wider so we can see things a little more here. And then you have also defective given that it's 2 and not defective given that it's 2. Write down each of those probabilities. You can write them down with percentages if you want. And then work out what this is. Come up with some symbols for these. Come up with symbols for these. Use that conditional formula if you want. Have you got some of the numbers filled in? Yeah. Okay, it says 70% of the chips come from factory 1 and 30 from factory 2. So if you just pick up a chip at the end, this is a 70% here. 70%. This is 30%. Once you know you're in that, once you know you're in factory 1, what's the chance of it being defective from factory 1? 25% of the chips are defective in factory 1. This is 25%. Which means, what is this number right here? It has to be 75% because that's the only other choice. How many are defective in factory 2? 10%. So this is 10%. This is 90% then. If you fill out those numbers, that's a good starting point here. It says then, suppose it is not known which factory it came from. What's the probability it's defective? With symbols, it's probability if it's defective. You don't know anything about where it came from. You got to work out the possibilities. What are the possibilities here? It could be 1 and defective. I'm just looking 1. 1 and defective plus 2 and defective. Right? You can work out each of those. You can work out each of those by multiplying. If you multiply each of those, what do we get here? We have 1 and defective is the end of this branch here. 70% times 25%, I believe it's 17.5%. This is 17.5%. Where's the other branch that we're looking at here? 2 and defective, this one, right? 30% times 10% is 3%. We're obviously going to need to come back to that